Hello everyone. Quantum entanglement has a long history of controversial interpretations, but fortunately, we are beginning to understand it better. For a long time, this concept was presented as a quintessential feature of non-classical behavior. The story used to go like this. On the one hand, there is a large class of physical properties that are known to be classical. These properties are easy to understand by human minds, and they all obey the famous Bell inequalities. On the other hand, there is also a strange class of physical properties that must be described as non-classical. These properties cannot be understood intuitively by human minds, and they are known to violate the Bell inequalities. In contrast, when we look at the facts as they are known today, we see a very different picture. On the one hand, we have observable properties that are expressed by physical entities at the same time. For example, if we look at this playing card, we see that it has several properties. It has a number that can be odd or even. It has a color that can be red or black. It has one of four suits, and so on. The distinctive feature of these properties is that their distribution in a deck of cards cannot contain contradictions. As you will see below, this is why they can never violate the Bell inequalities. On the other hand, we can also have physical properties that are mutually exclusive. Therefore, such properties cannot exist at the same time. They can only manifest in sequence. For example, this arrow can be oriented up or down along the vertical axis. It can point to the left or to the right on the horizontal axis, and so on for any axis in between. Yet, when we look at the pairwise coincidences between such properties, we can detect combinations that are impossible for properties that exist at the same time. Therefore, sequential properties are naturally able to violate the Bell inequalities. As you can see, we have two types of classical properties, and both of them can be found at any level of physical activity, from quantum to cosmic. Simultaneous properties cannot display Bell violations, but sequential properties can. There is no magic, no action at a distance, and no quantum weirdness to be found here. Indeed, any suggestion to the contrary is most likely a result of human error. Let us try to understand this concept in greater detail. First of all, why do some properties obey the so-called Bell inequalities? I find it easier to answer this question with a visual illustration. Suppose that we have a warehouse full of shirts. We want to study the relationship between these properties: fabric, color, and sleeve length. Suppose that we inspect all the shirts one by one and discover the following rules of coincidence. Number 1, all the cotton shirts are white. Number 2, all the white shirts are short-sleeved. If you take a moment to look at these rules of combination, it should become obvious that the third rule is logically fixed as well. The only possible scenario is that 3, all the cotton shirts are short-sleeved. Indeed, it would be some kind of miracle if we could find even one shirt that was made from cotton and had long sleeves, given the other two conclusions. Something like that is logically impossible, and therefore we cannot expect it to happen in real life. In short, simultaneous properties cannot avoid limiting each other's patterns of combination. They must always be compatible with each other. This is the grain of truth that is captured by the famous Bell inequality. Indeed, this is also what we see in typical presentations about Bell experiments, where four properties are chosen in order to test the so-called CH-SH inequality. When we make pairwise measurements in a chain, we see that the values of four observables are determined already after measuring just 3 patterns of coincidence. Just like in the example with shirts, the rule of coincidence for the last pair is automatically fixed. In this case, we expect to have 4 strong correlations, and all the coefficients are equal to +1. If we plug these coefficients in the CHSH inequality, we see that 1 + 1 + 1 - 1 equals 2. By the way, it is not necessary for all the coefficients to be equal to +1, but the point is that we cannot achieve a final result higher than 2 no matter how we choose them. Because they are mutually dependent, these coefficients can never violate the inequality. This is a mathematical fact. From a physical point of view, this is happening because all the properties are known to belong to individual objects at the same time. So, when we study 4 properties, we get a group of 4 coexisting values, even if we observe only 2 at a time. This means that one and the same value for one property is used in all the combinations with all the other properties of the same object. In contrast, when we have properties that cannot exist at the same time, then we get staggered manifestations. Suddenly, the pairing of events can happen according to more relaxed rules. For example, we see in this drawing that event B is closer in time to the value of A at t1, but event D is closer in time to the value of A at t5. So, if we measure pairs of events in small windows of coincidence, we can achieve combinations that are impossible for simultaneous events. In the left table, the value of A cannot be different in alternative combinations, but in the right table, it can. Let us take a moment to see what happens when we follow a sequence of staggered events. What we get here is a pattern that unfolds as if it is on a Mobius strip. First, we get 3 compatible coincidences just like in the previous example: AB, BC, and CD. Yet, here we cross over to the outer circle. Afterwards, we continue recording pairs of events until the cycle closes back on itself after the second loop. Notice that the order of events is fixed in advance, and we have pairwise consistency throughout the process, yet we still obtain a mixture of incompatible coefficients of correlation. 3 pairs of events are strongly correlated, but the last pair is strongly anti-correlated. If we plug these values into the CHSH inequality, we get 1 + 1 + 1 - -1, which gives 4. Not only did we violate this Bell-type inequality, we managed to achieve the maximal value that is theoretically possible, far beyond the quantum limit. In other words, it is impossible to falsify local realism by using a quantum Bell experiment. For a long time, such a conclusion seemed unthinkable because of Bell's theorem. So let me explain what is going on in brief. Bell's inequality is a very straightforward mathematical argument. It says the following: if we have a physical system that obeys the locality criterion, then the properties of the same system cannot violate the corresponding Bell inequality. In short, if locality, then Bell's inequality. It is because of this argument that quantum theory is described as non-local. We know that quantum properties violate the inequality. Therefore, it appears that we must also believe in a violation of locality. As it turns out, however, Bell's theorem is a false argument. Here is what happened. Bell started his argument with the locality criterion. Nonetheless, his demonstration involves an additional condition that is usually taken for granted in this context. This is the simultaneous existence condition, also known as the Einstein realism condition. It requires all the observables to be real at the same time from the source. So, the actual structure of the argument is like this. If the locality criterion applies, and if the simultaneity criterion is satisfied, then we get Bell's inequality. Notice I have just shown you that the locality criterion produces maximal Bell violations because sequential properties can also be local. So this condition cannot be used to derive Bell's inequality. In contrast, we have also seen a few minutes ago that simultaneous properties cannot violate the Bell inequalities. Therefore, this condition is the true source of Bell's conclusion. The nuance here is that simultaneous properties cannot influence each other directly. They have no time for that because they exist at the same time. So, the simultaneous existence criterion automatically presupposes locality, but the reverse is not true. Locality is a wider concept. In other words, we always have locality when Bell's inequality applies, but we can also have locality when it does not apply. We can express this graphically like this. Simultaneity is a small circle inside the bigger circle that represents locality. Accordingly, Bell's inequality applies in the smaller circle and only in this smaller circle. Obviously, it cannot be used to falsify the totality of local phenomena. To sum up, Bell's inequality does not follow from the locality criterion. It follows from the simultaneity criterion, which was not acknowledged by Bell. Yet, the stated claim of Bell's theorem is that his inequality follows from the locality criterion. This is why Bell's theorem is false. Strictly speaking, it does not contain any mathematical errors, but it is a false argument about locality. If you want a more detailed analysis of this problem, I recommend watching this lecture, The End of Quantum Non-Locality, which I produced recently. Today, however, I want to focus on a few related topics that are both interesting and important. First, I want to dispel a few misconceptions about the nature of Bell correlations. Secondly, I want to explain the mechanism behind quantum monogamy and to emphasize the combinatorial nature of Bell violations in general. Thirdly, I want to dedicate some time to the physical difference between the so-called quantum and super-quantum correlations. And finally, I will do my best to explain the mechanism behind quantum Bell violations with an intuitive example. There is a common misconception that quantum correlations are somehow intrinsically non-local. For example, Alice makes a measurement and obtains a result such as plus. In parallel, Bob makes an identical measurement on an entangled quantum and, surprise, surprise, he also gets a plus. If this happens consistently, we have a strong correlation, of course, but there is nothing unusual or paradoxical about this. Coincidences of this sort are very common in classical physics and indeed in our daily life. So it is misleading to describe any pair of quantum events as non-classical just because they are correlated. The technical nuance here is that Bell's inequality is not about raw coefficients of correlation. It is about relationships between coefficients of correlation. For example, when we do a Bell experiment, we can select 4 properties for a chain of pairwise measurements. We obtain 4 coefficients of correlation and then we add them together according to this formula. More importantly, we get the same range of values for our coefficients when the inequality is obeyed and when the inequality is violated. The coefficients can only have values between -1 and +1. Granted, the sum S can be 0 when the coefficients are weak, but we cannot violate the inequality just because the coefficients are stronger. So, there is no such thing as stronger than classical correlations. Instead, what is happening here is that we can have two types of physical qualities, compatible or incompatible. If we are dealing with properties that exist at the same time, or can exist at the same time, then we get compatible coefficients of correlation. For example, we can get 4 coefficients with +1 values or 4 coefficients with -1 values. We can also get 2 positive and 2 negative coefficients. What we cannot have is a combination of 3 positive coefficients and 1 negative coefficient. If our properties exist at the same time, then such a combination is impossible because our observables would contradict themselves. As we have just seen, if we have an experiment with 4 variables, we can determine the values for all the observables after measuring just 3 pairs of coincidences. Therefore, the fourth pair is automatically determined. Thus, if 3 coefficients have a value of +1, then the last one can only be +1 as well. Yet, when we process these values according to the CHSH protocol, we cannot obtain a result that is larger than 2. In this case, the easiest way to achieve a result larger than 2 is for our last coefficient to be smaller than +1, other things being equal. In other words, we do not get Bell violations by achieving stronger correlations. Instead, it is more accurate to say that some coefficients are weaker than they should be. Basically, our coefficients swing in the wrong direction, so to speak. And so, to sum up, it is incorrect to describe Bell violations as the result of stronger coefficients of correlation. Bell's inequality is not a test of correlation. It is a test of compatibility between several coefficients of correlation. When physical properties cannot exist at the same time, they can be incompatible with each other, and for the same reason, their coefficients of correlation can also be incompatible with each other. Some people might listen to this and say, sure, quantum coefficients are not always stronger, but they are stronger than classical coefficients in special cases. For example, suppose that Alice and Bob perform a polarization experiment with entangled photons. If the quanta are prepared to be polarized in one plane, and Alice measures the photons in the same plane, it is normal to achieve strong correlations. However, Bell experiments are rotationally invariant. This means that Alice does not know the state of the incoming quantum. She can choose to measure in any arbitrary plane of polarization, and she will always detect an outcome that is also expected by Bob for the same measurement. More importantly, Alice and Bob can choose to measure different planes, and their correlation will always be determined by the difference between their chosen plane of observation. In other words, it may seem that quantum correlations are similar to classical correlations, but they appear to manifest in a manner that is classically impossible. This argument sounds impressive, and many people found it persuasive in the past. Nonetheless, it is incorrect. The important detail here is that Bell experiments are not about individual results. They are about correlations after large numbers of observations. When we measure classical systems, individual outcomes are not rotationally invariant. Indeed, they cannot be rotationally invariant both in classical and quantum physics. After all, some types of outcomes are mutually exclusive. In contrast, coefficients of correlation can be rotationally invariant without metaphysical interventions. To illustrate the point, let us consider two identical strings of numbers. Alice has a string that reads 0, 0, 0, and the same sequence is available to Bob. Next, we send both of them identical instructions. For example, flip all the numbers from 0 to 1. As a result, Alice and Bob have different sequences compared to the starting profile. Yet both of them have the same sequence, 1, 1, 1. Therefore, their systems are perfectly correlated. It should not be hard to realize that we can send Alice and Bob as many instructions for change as we want in any order. Every time, their outcomes will change. However, they will always get strong correlations because they will always get identical outcomes. This freedom of transformation is what corresponds to rotational invariance in polarization experiments. In short, when we deal with classical systems, if we start with identical properties and perform identical transformations, then it is only logical that we should get identical outcomes. This is true for any rule of transformation that we might choose. For this reason, it is fair to extend this conclusion to rotational invariance in Bell experiments. We do not even need to know the input state for this to hold. The trick here is to remember that we are talking about coefficients of correlation, not about individual outcomes. The properties can change, but the correlations can persist in adequate conditions. Furthermore, we can choose not to send identical instructions for transformation to Alice and Bob. In this case, again, it does not matter what the instructions are. As long as we care about the coefficients of correlation between Alice and Bob, the only factor that matters is the net difference between the instructions that we send to our observers. For example, suppose that Alice and Bob have identical starting sequences, such as 0, 0, 0. We can ask Alice to change the first and the last number, while Bob is instructed to change the first and the second number. This time, Alice gets 1, 0, 1, while Bob gets 1, 1, 0. The instructions are very different, but the net difference is only determined by the difference between the two instructions, no matter how complicated these instructions may be. Accordingly, when we have identical or highly correlated classical systems, we can transform them in arbitrary ways. If the rules of transformation are nearly identical, the output states are going to be highly correlated. If the rules are increasingly different, the correlation at the output will gradually diminish. It does not matter what we do to our systems as far as the correlations are concerned. The final relationship between the outcomes is determined by the difference between the so-called measurement settings. To sum up, we can have rotational invariance for identical transformations, and we can also have rotational invariance for non-identical transformations. At no point do we have a reason to see this behavior as non-classical. The fallacy was to think about individual outcomes. Yet, Bell experiments are meant to study relationships between coefficients of correlation. Of course, the claim here is not that classical transformations are always invariant. The point is that they can be invariant in adequate conditions. Therefore, such patterns of behavior cannot be described as automatically non-classical, even at the quantum level. Finally, another reason to describe quantum correlations as non-classical is purely semantic. In some definitions, classical physics is a term that applies to all the knowledge that was obtained prior to the year 1905. Therefore, some processes are described as non-classical simply because they were not considered before modern physics. Any classical phenomenon that needs to be reconsidered is automatically described as non-classical. Any application of modern tools, including the formalism of quantum theory, is automatically described as non-classical. In short, we have a rhetorical trick based on the perceived false equivalence between classical tools or methods and classical laws of physics. For example, pre-modern textbooks described polarizing devices as if they were passive filters. Presumably, Optical projections contain many different components with different polarization from the source. The polarizing beam splitter is just a filter that reflects some components and allows others to pass through. It causes no perturbation. So, in this case, we cannot accept the appearance that an optical beam is diagonally polarized from the source. We have to describe it as a coherent mixture of two components, vertical and horizontal. Yet, as we know today, quantum observables are contextual. We cannot make correct predictions if we assume that output qualities, such as vertical and horizontal polarizations, existed as individual quantum properties from the source. Accordingly, it seems that we cannot use a classical model to explain the result of a quantum experiment. Yet, the problem here is not that classical mechanics is limited. The problem is that all the methods in classical physics were mathematically accurate but physically misleading. For example, imagine that we have a rope agitated in the diagonal plane. The waves are propagating from left to right. Then we introduce a rigid frame that acts as a slit. If the slit was anti-diagonal, the waves would have been blocked. Yet our slit is vertical and the waves continue to propagate with a reduced amplitude. You see, we can describe the input polarization as the vector sum of two components, one vertical and one horizontal. This is mathematically correct, but what is actually happening in real life? Is the rope moving in two directions at the same time? No, this is just an abstraction. The rope is only oscillating in the diagonal plane. Therefore, the correct physical interpretation is that the wave is not filtered by the narrow slit. We have a physical interaction in which the plane of oscillation is rotated and the final outcome is predicted by this vector sum if and when it happens. In other words, we get a contextual property at the output because the wave suffered a transformation during the interaction with the slit. The wave was really diagonal at the input and it is really vertical at the output. Accordingly, there is nothing fundamentally quantum about contextual properties. Indeed, we can take this feature into account when we explain correlated measurements. As we saw a few minutes ago, it is perfectly normal in classical physics to start with identical inputs, followed by identical transformations, in which case we get identical outcomes for Alice and Bob. In this case, the photons can be prepared to be identical at the source, followed by identical microscopic transformations and leading to identical detection events. In short, contextual properties are perfectly classical, and there is nothing unusual about their correlations. We just need to understand the rules that govern their patterns of manifestation. Another way to illustrate this problem is by using the example of pilot wave models. Quantum dualism was a shocking discovery, inspiring a fervent search for meaningful explanations. One of the earliest such proposals was the pilot wave theory of Louis de Broglie. Strictly speaking, this is a model that emerged in the context of quantum mechanics and was primarily applied to quantum behavior. Nonetheless, there is nothing fundamentally non-classical about a particle surfing a wave. For example, we can use the formalism of quantum theory to study the distribution of human surfers in a stable wave pattern of practical size. We know that surfing is not possible where wave amplitude is zero, and it is more and more successful where wave amplitude is higher. So, we can use the statistics of surfer detection to infer the distribution of wave amplitudes in chosen planes of detection. Note that the theoretical tools for studying such behavior were formulated in modern times. Nonetheless, it would be misleading to describe this behavior as automatically non-classical just because we can use the formalism of quantum theory in such cases. With this in mind, let us review what we have just discussed. First of all, it is incorrect to describe quantum correlations as stronger than classical correlations. Bell experiments are tests of compatibility, and violations happen when coefficients are mutually exclusive, not when they are magically stronger. It is not possible to have correlations that are stronger than the modulus of plus or minus 1. Furthermore, it is also not correct to suggest that quantum correlations are stronger in special conditions. Such claims are based on various misconceptions. In particular, it is not true that rotational invariance is non-classical, and it is equally false to suggest that contextual properties are somehow weird or spooky. When we pay attention to the subtle aspects of the relevant concepts, we see that non-classical interpretations are almost always rooted in confusion. Though, as we shall see below, there is an important difference between individual behavior and system-level behavior. Sometimes, single objects express systemic properties, which is what we see in the case of quantum superposition. Yet, this is also classical behavior, ontologically speaking. We just did not have the tools to study such behavior in pre-modern times. Over the years, the stories about non-locality acquired a life of their own, so much so that the basic underlying concepts appear to have been forgotten. For this reason, it often seems that quantum theory and statistical theory are at odds with each other. This is why I think it is appropriate to review a few basic definitions in this area. When we talk about random variables, we can describe them as statistically dependent or statistically independent. Statistical dependence simply means that our two variables are correlated. The result is that their joint distribution becomes inseparable. To be clear, when we have statistical independence, joint probability distributions can be factorized, as shown in this expression. In contrast, if our variables are statistically dependent, then joint probability distributions cannot be factorized. However, it is important to note that correlations do not carry physical implications. Just because we have correlations, it does not follow that we have direct influences between our events. Of course, it is possible for such influences to exist, but this is not necessary. Accordingly, statistical theory contains another concept known as conditional independence. In some cases, it is possible to identify a set of conditions that serve the function of a common cause. If we take these parameters into account, we can factorize the joint distribution even if we have strong correlations. Hence, we can write this equality as shown on the screen. It should not be hard to notice that this is the relationship that Bell described as the locality criterion. Indeed, if our variables do not influence each other directly and instead have a common prior cause, then we can describe them as local. In other words, we have statistical dependence and physical independence. My point is that the concept of separability, as used in quantum mechanics, does not mean unconditional separability. Instead, the concept of locality is only relevant for discussions about conditional separability, given the observation of correlated events. So now we get to the million-dollar question. If we have a set of variables that are statistically dependent, but we cannot inspect their causal roots, can we use mathematical tools to determine if they are conditionally independent? As a consequence of Bell's theorem, many people were convinced that the answer is yes. If we process the coefficients of correlation of a Bell-type inequality, we can rule out conditional independence and therefore locality for a large class of relevant phenomena. Accordingly, it appeared that Bell broke new ground in statistical theory. However, today we know that this is not true. Bell's inequality can be used to identify jointly distributed variables, but it cannot tell us whether or not we have conditional separability in general. So, what can we do instead? The textbook answer is to pay attention to the order of events. First of all, if we have events that happen at the same time, then it is logically impossible for them to influence each other directly. Any causal influence would require time, which is not available in this case. So, we can only have influences between sequential phenomena. However, just because we have events that are staggered in time, it does not automatically follow that we have direct influences. In order to determine the underlying mechanism, we need to experiment with the order of events. For example, suppose that we have an event A followed by some other event B. After recording a fair sample of such instances, we can determine their coefficient of correlation. Then we can change the order of events and determine the coefficient of correlation for the reversed scenario. If we discover that the two results are not equal, then we have non-commutativity. Therefore, it makes sense to assume that our events influence each other directly. However, we have to be very careful. Which relationship is known to be non-commutative? If we look at different properties of a single system, it is possible for some operations to commute while others do not. Therefore, we should not be quick to invoke direct causality just because we are working with non-commuting variables. The only parameter that matters for our questions about causality is whether the coefficients of correlation are sensitive to the order of events. For example, let us consider a classical optical projection. We have an unpolarized beam that is passed through a sequence of two polarizing filters. Suppose that the axis of the first filter is 0 degrees from the vertical plane, while the axis of the second filter is inclined at 22.5 degrees. The known feature of sequential measurements of polarization is that they obey Malus's law. In other words, the proportion of transmitted beam energy is determined by the cosine squared of the angle between the two polarizers. And so, in this case, 50% of the input beam will pass through the first polarizer, becoming vertically polarized. Then 85% of the transmitted portion will be transmitted again through the second polarizer. Hence, the rate of identical coincidence between the two measurements is 85%, with a final coefficient of correlation of plus 0.7. More importantly for our discussion, this coefficient does not depend on the order of events. Before I go into other details, allow me to explain why this example is important. Classical beams obey Malus's law, which means that they are automatically able to violate the Bell inequalities. After all, this is exactly the pattern that we see in quantum experiments as well. This is not surprising because quantum mechanics obeys the so-called correspondence principle. Large number of quantum events converge on the same patterns that are observable with classical projections. So, we have a demonstration that is obviously classical, yet somehow our textbooks insist that Bell violations cannot be classical. What is going on? The answer is that classical measurements of polarization do not commute. If we start with a measurement at 0 degrees, followed by a measurement at 22.5 degrees, then the final output is polarized in the 22.5 degree plane. If we change the order of measurements, then the final output is vertical. Furthermore, if we modulate the setting of the first polarizer, then the probability of a transmitted event at the second polarizer is directly affected. So the order of events has a direct effect on the final result. Therefore, the automatic assumption was that we have a causal influence between the first measurement and the second. Accordingly, we can have Bell violations in classical physics, but the presumption was that we cannot have locality. Moreover, because we see how these measurements influence each other, we have to assume that quantum measurements also influence each other, even if they are conducted in parallel and even if they are separated by cosmic distances. In short, classical measurements appear to strengthen the case for non-locality instead of weakening it. Yet, things are not always what they seem. I have shown you a few minutes ago that we can only determine the reality of direct influences between events if their joint probability is affected by the order of events. In other words, it does not matter what other operations are possible and whether these other operations commute or not. The only thing that we can determine with confidence in a Bell experiment is the coefficient of correlation. So the question that we need to ask is whether the coefficients of correlation between two variables depend on the order of measurement. Let us return to our example with an unpolarized classical projection. We can test what is going on with two experiments. First, we polarize the beam in the 0-degree plane, then rotate it to the 22.5-degree plane. The proportion of the beam that is transmitted or reflected in the same way through both stations is 85%. Second, we can set up the experiment such that the 22.5-degree setting is first and the 0-degree setting is second. In this case, we see again that the proportion of transmitted or reflected radiation is 85%. In other words, the order of events has no effect whatsoever on the coefficients of correlation between these two measurements. Allow me to give you a different example in order to clarify the intuition behind the concept of causal dependence. Consider the following situation. Event A1. I watch a short video about donation scams. Event B. I receive a request to make a donation for some humanitarian cause. Now consider an alternative scenario. Event A2. I watch a video about an impressive social result produced by a number of modest donations. Event B. I receive a request to make a donation for a similar cause. It is a known pattern in psychology studies that preceding events like A1 decrease the probability of donation, while preceding events like A2 increase this probability for the same individuals. Yet, the relevant question for us is this: what is the mechanism behind this effect? The relevant nuance here is that sequential events can influence each other in two ways. Event A can control the input for event B, and therefore it has an effect on the output, but it does not affect in any way the mechanism of transformation associated with the second phenomenon. In this case, we can expect the correlations between the two events to be unaffected by the order of events, because the mechanism of transformation for event B is not affected by event A. Yet, in our example with donation requests, we have something else. Events A1 and A2 have a direct effect on the process of evaluation for each decision. Hence, we have the same input in both cases, a request for donation. Nonetheless, the outcome is different because the input is not processed in the same way in both cases. More importantly, The order of these events is crucial. If I consume opinion-altering information after my donation, the final result is very different. Now, let us return to our polarization example. What do we know about polarization devices? The answer is that they always obey Malus's law, at least in ideal conditions. So, if the input is the same, the output of these devices is always the same. In contrast, if we use other devices to modulate the input, then the output can become different, but not because of some change in the operation of optical polarizers. Indeed, the output is different because the effect of the polarizers is consistent throughout. Accordingly, if we have two polarizers in a row, we cannot claim that measurements influence each other. The exact output may be affected, but the coefficients of correlation are the same in any order. To sum up, we can only claim to have measurement dependence if there is a direct effect on the mechanism of measurement. Still, we do not have to stop here. We can ask, is there a more direct way to confirm that we have independence between sequential transformations of polarization? The answer is yes. We can choose to make two copies of our objects and to make parallel transformations instead of sequential transformations. For example, if Bob makes the 0-degree measurement, he gets a 50-50 distribution. If Alice makes the second measurement at 22.5 degrees, she also gets a 50-50 distribution. Though, if the correlations are not due to measurement interactions, then the final coefficients can still be the same, just as in the case of sequential transformations. Indeed, what we see in quantum Bell experiments is that parallel measurements produce the same correlations that we see in sequential classical measurements. Therefore, quantum Bell violations confirm the absence of direct influence between our devices. This is quite an interpretive reversal. To sum up this discussion, we cannot use Bell's inequality to verify the reality of conditional separability. We can only do this by changing the order of events in order to see if the coefficients of correlation are affected. If the order of transformation does not matter, and especially if the coefficients stay the same in parallel measurements, then our properties are physically independent from each other. This conclusion brings us to another important misconception about quantum correlations. When we see presentations about some Bell experiment, the tendency is to start the discussion with details about remote measurement interactions. First, we hear arguments about action at a distance. Then we hear speculations about loopholes and the technical requirements to close them. As a result, it is too easy to forget what is actually going on in a typical correlation experiment. So let us go back to the basics yet again. When we look at an everyday object, such as a playing card, we notice several properties at the same time. For example, we see that the number is odd or even, the color is red or black, and so on. This tells us that a deck of cards might display some sort of relationships between such properties. It may be that the suit of the card is correlated with its color, but other properties might be independent. Indeed, we can inspect all the cards in a deck and determine all the coefficients of correlation that we care about. Yet, we know that the properties of these cards exist at the same time. Therefore, they cannot violate Bell's inequality. Allow me to repeat. The properties of a single system are such that here, inside the system, Bell violations are impossible. Now, let us imagine that we have two identical decks that are stacked in the same order. Every time we pull two cards at the same time, we get the same image from both decks. Therefore, we can now do a trick. We can use one card to measure one property, and we can use the other card to measure the second property. Obviously, it makes no difference if we use the left card or the right card for each measurement, because they are identical. You see, we can use two remote measurements to do a Bell test, but fundamentally, this is not a relativistic phenomenon. The distance does not matter at all, because the cards are identical. The basic reason why we get Bell's inequality with two remote measurements is that each system individually obeys Bell's inequality. Then, because of the similarity between the two systems, we can reproduce the same patterns with coincident measurements at a distance. The question is, can we have the same type of behavior when we get Bell violations? Well, let us consider a simple classical object, such as a rotating arrow. At any moment in time, the arrow can cross one of several imaginary axes. For example, if it crosses this axis when it points up, we can call it a plus, and if it crosses it in the opposite direction, we can call it a minus. In the same way, we can choose other axes with assigned values similar to what we see in discussions about electron spin. After choosing 4 suitable axes, we can divide the plane into sectors to assign properties for a Bell-type experiment. The arrow can be programmed to rotate, passing through each sector one at a time. Therefore, all the properties are mutually exclusive, even though they are all predetermined in advance. We can call A1 and A2 Alice events and B1 and B2 Bob events. It should be easy to notice that Alice and Bob events are interlaced such that any Alice event can be paired with either one of Bob's two events, given a short window of coincidence. Of course, the same holds for Bob. As you can see, it is impossible to have interactions between these events because all the values are printed in advance and cannot change. Yet, despite this obvious independence, we can achieve all the pairings that are required for a Bell experiment. Furthermore, if we look at all the possible coincidences in sequence, we get a fixed cycle of events that can be repeated as long as necessary for statistical significance. The end result is that our arrow will display properties that produce maximal Bell violations. This is the same pattern that we discussed at the beginning of this slideshow. 3 pairs of variables can only coincide with identical signs, while 1 pair can only coincide with opposite signs. This produces an incompatible mixture of coefficients, leading to a maximal Bell violation. This means that we can make 2 identical systems with 2 arrows and spread the measurements between the 2 stations. As long as our systems are identical and perfectly synchronized, we should expect the same result as if we conducted all the measurements locally as part of a single system. Just as we saw with playing cards, the 2 arrows can be in the same room or in different galaxies. It makes no difference because there is no communication between them. We just need Alice and Bob to record the time of each event and come together afterwards to reconcile their records. In short, the simultaneous properties of playing cards are such that they always obey Bell's inequality as part of a single system. Because of this, experiments with identical copies of the same system cannot observe Bell violations. In the same way, the sequential properties of rotating arrows are such that they violate the Bell inequalities as part of a single system. So, if we make 2 copies of such systems, we can achieve the same pattern in a Bell experiment. In both cases, we see relationships between the properties of single systems. We have no reason to speculate about possible remote interactions across the systems. With that in mind, let us summarize what we have seen in this section about correlation basics. Physical events can be statistically separable if they are random and statistically inseparable if they are correlated. However, this distinction is irrelevant for discussions about the nature of quantum correlations. Instead, we care about the combination between statistical inseparability and physical separability, which corresponds to statistical conditional separability. Contrary to Bell's theorem, it is not possible to determine the reality of physical separability with a Bell test. Instead, this can only be done by changing the order of measurements. Notably, quantum correlations are determined with simultaneous parallel measurements. Hence, it is not surprising to discover that they are conditionally separable and therefore local. Finally, once we determine if the order of events is consequential, Bell violations cannot add anything to this discussion. The ability to violate or not to violate such inequalities is entirely determined by the relationships between the properties of single systems. If we get violations as part of a single system, then we can also expect them for pairs of clone systems. This cannot tell us anything new about the dependence or independence of relevant variables. And now that we have clarified so many basic concepts, we can move on to more advanced aspects of this problem in part 2.